Hello all, welcome back to Electronic Device and Circuits video lecture series. I am BVV Sachinarayana, Associate Professor in Department of ECE, Vishnu Institute of Technology, Bhimavaram. Unit number 5 of Electronic Device and Circuit subject is transistor biasing and thermal stabilization. In this unit, we will discuss what is transistor biasing and what are the three methods of biasing the transistor, such as fixed bias, collector to base bias, and self bias. Then calculation of operating point and stabilizations. And at the end of this unit, we are trying to discuss the methods of biasing the FET. Introduction. The objectives of this video are need of transistor biasing, DC load line and analysis, and what is operating point. Need of biasing the transistor. The process of externally applying DC voltages to operate the transistor is called transistor biasing. Basically, transistor is a 3-terminal, 3-region and 2-junction device. The 3 terminals of the transistor are emitter, base, collector, and the 3 regions are emitter region, base region and collector region. The 2 junctions are emitter junction and collector junction. Emitter junction we can call it as a input junction, and collector junction is called the output junction. We can operate the transistor in any one of the 3 regions, such as cutoff region, active region and saturation region, by applying proper biasing conditions. Emitter junction, collector junction, region of operation and obligation. Suppose if emitter junction is forward biased and collector junction is reverse biased, then the transistor is said to be operated in active region. Then the transistor can be used as an amplifier. If emitter junction is reverse biased and collector junction is also reverse biased, then the transistor is said to be operated in cutoff region. Then the transistor can be used as a off switch. If the emitter junction is forward biased, collector junction is also forward biased, then the transistor is said to be operated in saturation region. Then the transistor can be used as a on switch. Suppose if the emitter junction is reverse biased and collector junction is forward biased, then we can call it as a inverted case. Why? Because the transistor is a current control device. So as to operate the transistor, we need to supply some input current. Here the emitter junction, input junction is reverse biased, means no current is supplied and hence the transistor it never operated. That's why we are calling it as a inverted case. It is never used. So to operate the transistor in required region, we need to bias the transistor. Suppose I wanted to use the transistor as an amplifier, then the emitter junction must be forward biased and collector junction must be reverse biased. In order to operate the transistor in the desired region, we have to apply external DC voltages of collector polarity and magnitude to the junctions of the transistors. This is called biasing of the transistor. Since DC voltages are used to bias the transistor, this is called DC biasing of the transistor. The purpose of this DC biasing of a transistor is to obtain a certain collector current IC at certain DC collector voltage VCE. These conditions are known as the operating conditions of the transistor. These values of IC and VCE are expressed by a term called operating point, Q-cent point or Q point. So by applying these external voltages, we are setting VCE and IC, and the transistor is operated so that that particular point we can call it as a operating point. So to obtain the operating point, we make use of some circuits, and those circuits we can call it as a biasing circuits. Yeah, while fixing the operating point, it has been said, it has to be seen that the biasing circuit must provide proper DC conditions so that the transistor can be operated in a specific, operated in a particular region, and it can perform the specific function. The operating point must be stable for proper operation of the circuit. Once the operating point is fixed, it should be stable. It cannot move. But the operating point shifts with changes within transistor parameters such as beta, IC0, and VBE. So all these transistor parameters are temperature dependent. So the operating point varies with changes in temperature. So the biasing circuit must provide thermal stabilization against the temperature variations. Means even though there are some changes in temperature, there must not be any change in operating point. Then only our transistor can be properly operated. So to operate the transistor in the required region, to fix the operating point, and to stabilize the operating point, we need biasing for the transistor. Then DC load line and operating point. So now I am trying to define what is DC load line and what is the operating point, and how can we draw the DC load line, and how we can obtain the operating point. Consider a transistor which is connected in CE configuration. And for this transistor, the emitter junction JE is forward biased, and the collector junction JC is reverse biased. Let me draw the circuit diagram. I am assuming the transistor is connected in CE configuration. This is the transistor which is connected in CE configuration. Now the emitter junction is forward biased. Means this is emitter terminal, base terminal, and the collector terminal. So emitter junction must be forward biased. So the base emitter junction is connected to a power supply through a resistor. So that power supply we can call it as a VBB. This is the common terminal, emitter terminal, that should be grounded. So this base emitter junction is forward biased with this VBB through a resistor, current limiting resistor called RB. Similarly, the collector junction must be reverse biased. So the collector is connected to a power supply through another resistor. We can call it as a load resistance RC, or we can represent it as a RL. RC itself can be used as a RL, that is connected in the output circuit, collector circuit. This junction, it must be reverse biased with VCC. This is VCC. Emitter junction is forward biased by VBB and collector junction is reverse biased with VCC. Now, because of this VCC, we are getting a current in the output circuit. That current I am representing it as a IC. So because of this IC, we are getting some voltage drop across RL or VC. That drop we can represent it as IC into RL or RC. In VCC, some voltage is dropped across RC and the remaining voltage will appear across the transistor, that we are representing it as a VCE. In CE configuration, we can call it as a output voltage. Similarly, in the input circuit, there is a battery VBB, and because of this, we are getting some current called IB, and that IB is flowing through RB. So some voltage is dropped across this RB, and the remaining voltage it will appear in between base and emitter, that is VB. So with this circuit setup, we can easily obtain the DC load line, and from that we can easily obtain the operating point. So apply KVL to the collector circuit. Apply KVL to output circuit or collector circuit. Then VCC equal to ICRC plus VCE. From this, IC equal to VCC minus VCE by RC. Then rearrange this equation such that IC equal to minus 1 by RC into VCE plus VCC by RC. So this is equation 1, equation 2 and equation 3. Now our equation 3 is in the form of y equal to mx plus c. So that I am calling it as a equation 4. Y equal to mx plus c. Means if you plot equation 3 on transistor output characteristics, then that equation 3 it represents a straight line. On output characteristics, equation 3 it becomes a straight line with slope equal to if you compare equation 3 and 4, we are getting slope that we are calling it as a m, which is equal to minus 1 by RC. That is the slope of the straight line. And the y intercepting point is C. So which is equal to VCC by RC. Now this straight line we can call it as a DC load line. The equation 3 it's a straight line, that we can call it as a DC load line. So how can we draw this DC load line? Means on VCE axis, on VCE axis means it's a x-axis, IC equal to 0. Similarly, on IC axis, VCE equal to 0. Then we are getting 2 points, 1 point on VCE axis and 1 point on IC axis. By joining these 2 points, we can obtain the DC load line. So substitute these two in equation 3, then we are getting 2 points. Suppose if IC equal to 0 in equation 3, then we are getting VCE equal to VCC. Similarly, if VCE equal to 0 in equation 3, then IC equal to VCC by RC. So we are getting 2 points. One is VCC on VCE axis, that is the x-intercept point. Another one, it is IC equal to VCC by RC, that is y-intercept point. So if you join these 2 points, then we are getting the DC load line. So you can write the points like this. So here IC y equal to 0 and x equal to VCC. So this point we can represent it as a VCC comma 0. So VCE, that is x parameter, which is VCE, and IC is 0. Similarly, the y-intercept point is here VCE equal to 0 means x equal to 0 and y is VCC by RC. So by joining these 2 points, we are getting a line called DC load line. DC load line. Let me sketch the characteristics. The output characteristics of a transistor are like this. So this is x-axis. This is x-axis. It is VCE axis, and this is y-axis. That is IC axis. Okay. VCE versus IC. It represents the output characteristics. We can draw the output characteristics by fixing the input current IB. So suppose if you assume initially IB equal to 0, suppose, then a very small leakage current is flowing through the transistor, that is for IB equal to 0. As we are increasing our IB, then the IC is also increases, so that we are getting our characteristic curves like this. So this is IB1 and this is for IB2 and this is for IB3 and this is for IB4. So as IB increases, IC is also increases. Now identify these 2 points, VCC comma 0 on x-axis and 0 comma VCC by RC on y-axis. So somewhere here we are having 1 point, that is VCC comma 0, and here we are getting another point, that is VCC by RC. So by joining these two, we are getting a straight line that we can call it as a load line. So this straight line is called load line, DC load line. So note that we are applying DC voltages, that's why it's a DC load line. So why it is called load line means the slope. What is the slope of this line? The slope of this line is equal to minus 1 by RC or RL. Means the slope of the line depends on the load resistance under DC conditions. That's why this line we can call it as a DC load line. DC load line. Yeah, the operating conditions of the transistor are described by the values of VCE and IC. So those operating conditions we can call it as a operating point. Operating point. The operating point of a transistor not only depends on the characteristics of the transistor, but also depends on the number of factors such as VCC, RC, VBB, RB, and VBE. All these parameters decides the operating point. Okay, in addition to the output characteristics of the transistor, all these parameters decides the operating point. Okay, so as to obtain the operating point, first fix VCC and RC. So by fixing these two values, we can ensure that the operating point of the transistor must lie on the DC load line. First fix the VCC and RC, and these two values ensures that the operating point lies on the DC load line. Why? Because we are getting DC load line with these two values, VCC by RC and VCC with those two values, we are getting the DC load line. So operating point, it is somewhere on the DC load line. Then the exact location of the DC load line is depends on VBB, RB, and VBE. On the load line, where exactly the operating point location is, that depends on VBB, RB, and VBE. Apply KVL to input circuit, then VBB equal to IBRB plus VBE. From this, IB equal to VBB minus VBE by RB. Or otherwise, we can write IB is approximately equal to VBB by RB if VBE is far greater than VBE or VBE value is very small. Now, by knowing the values of VBB, VBE, and RB, we are getting one value of IB, and sketch the output characteristics of the transistor with these values of IB. So let me draw the output characteristics again. This is voltage axis, VCE axis, and this is IC axis. Then first draw the DC load line. So the on x-axis VCE equal to 0, which is equal to VCC, and on y-axis IC axis VCE equal to 0, which is equal to VCC by RC, and by joining these two, we are getting the load line. This is the load line. Now, with this value of IB, sketch the output characteristics. then we are getting the output characteristics like this. Then this IB curve intersecting with the load line, then that intercepting point we can call it as a operating point or Q point or Q-center point. The exact operating point will lie at the intersection of IB curve and the DC load line. So at this point, the corresponding VCE value and IC value, it gives the operating point, Q point. Q point means it is simply the values of VCE and IC. So likewise, we can find the operating point. So no doubt that the operating point must lie on the DC load line only. Then coming to the summary. In this lecture, we have learned the following. Need of transistor biasing, what is DC load line and analysis of DC load line, and what is the operating point and how we can obtain the operating point. Thank you.